Hello, in this video I'm going to be going over orbital filling diagrams. So first of all, here is an example. We have silicon, and as I draw an orbital filling diagram for silicon, I'm showing each suborbital and how many electrons can fit in each. According to the Pauli exclusion principle, I can have no more than 2 electrons in each suborbital, and they need to have opposite spin. Alright. What I usually do is I write the electron configuration first, and then it kind of helps me kind of plan out how many boxes and what order I need to make them. So it's important to remember that the s orbital is going to have 1 box, or you could draw a circle. The p orbital is going to have 3 boxes together. You do not want to write it a box, a box, a box. That would not be good because it looks like 3 s orbitals. Can't do that. The d orbital then has 5 boxes together. 1, 2, 3, 4, 5. And each box represents a suborbital. The d orbital has 5 suborbitals. And then the f is going to have 7 boxes or suborbitals. 1, 2, 3, 4, 5, 6, 7. Alright, as I draw the electron configuration for silicon, remember I need my periodic table to help me out. I start at hydrogen. That's the Aufbau principle, building up. And it's in the first row, and we're in the S section. 1, 2, 1s2, helium being an exception. And then we're at number 3, lithium, 2s2, 1, 2, 2p, 1, 2, 3, 4, 5, 6. So we have 6 of these guys, 1, 2, 3, 4, 5, 6. And then we're in the third row, 3s1, 2. And then right over to still the third row, p section, 3p1, 2. Alright, oops. Now that we have the electron configuration, we can more easily draw the orbital filling diagram. So remember, the s's are represented by 1 box. So that's 1s2. And it's represented by 1 up arrow and then a down arrow. And that's the Pauli exclusion principle, states that no more than 2 electrons can be in each suborbital, and each has to have an opposite spin. Now we have the 2s2. Again, it's a single box. 2s2. Here, let's rewrite that. 1s2, 2s2, filled up. Now we're at 2p6. So remember, the p orbital has 3 sublevels, 3 suborbitals. 1, 2, 3. 2p6. 1, 2, 3, 4, 5, 6. Now, in order to follow Huebner's rule, you need to fill in each suborbital with 1 electron before you can fill it in with a second. That is Huebner's rule. And in this case, it's filled up to 6, so ultimately it doesn't matter. But for that 3p2, when we get to it, it is going to matter. Alright, next is 3s2. Up, down, 3s2. And then 3p2, since it's the p orbital, we do have to show 3 boxes, 3p2. However, we only have 2 electrons. And they are each filling in a box with just 1 electron. It's okay to have 1 that's empty. Something that you would not do, that would be absolutely incorrect, would be having 1, 2 in the same box. It would require more energy for that to happen. We're assuming that this is at a low energy state, a ground state. So we have to follow Huebner's rule, where each suborbital has to be filled with 1 before you can start filling them with a second. And that is orbital filling diagram for silicon. Alright, but since we have some time, why not do another problem? So we got vanadium right here. Again, doing the electron configuration is always helpful. First, so we have 1s, 2 again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d 1, 2, 3, and d's are always one less than the row they're in, so it's 3d, not 4d. Alright, so that's our electron configuration. Now we can do the orbital filling diagram. I'm going to start right here. And S, that 1s2 is represented by one box, up arrow, down arrow. 2s2, again, represented by one box, up arrow, down arrow. 2p6, 2p6. 1, 2, 3, 4, 5, 6, and it's filled up. Now we have 3s2, one box, up arrow, down arrow. 3p6, same deal. 3 boxes, all filled up. 1, 2, 3, 4, 5, 6. And then I have 4s2. 2. And I don't have enough room. I would draw it here, but I don't have enough room, so I'm just going to start another row. 1, 2, 3, 4, 5. And this is 3D, 3. I'm going to do 1, 2, 3 to follow Huebner's rule, show that each box needs to have one electron in it before you can add a second. That is the orbital filling diagram for vanadium. One last thing, counting valence electrons. When you have orbital filling diagram, it's the same as electron configuration. We have 3, 3, 3, 2, 2, 1, 4. 4 is the highest energy level, and that's the only one. We have 2 electrons in there, so we have 2 valence electrons. What if we do silicon? It's first energy, second energy level, third energy level. So the third energy level is the final energy level, outermost. So our outer electrons, we're going to have a 2 and a 2, which is 4 valence electrons.
So